This is the lecture for section 11.8 on power series. And to explain the main points about power series, I want to first work through an example. So here's an example that shows us the main idea in this section. So I want to consider the following series. So it's the summation n equals 0 to infinity of 1 over n times x to the n. And here x is a variable, right? So the series is summing n equals 0 to infinity, and x is just some number that you don't know what it is. And this series is going to converge for some values of x, and it's going to diverge for other values of x. So what we're interested in finding is the values of x that make this series converge. In other words, if you consider the left-hand side expression as a function, there are some x's that you can put in as an input and you'll get a number, and there are other x values that when you input you don't get a nice output value. And so what we're asking for is we're asking for the domain of this left-hand expression as a function. What are the allowable x values? Okay? And the way to think about how to find the x values that make this series converge is by looking at the form of the series. Right, so here we see powers of x, which is frequently our hint that we should be using either the ratio test or the root test. And so I'm going to try the ratio test for this one. So our absolute value of an is absolute value of 1 over n x to the n, which you can rewrite as 1 over n because n is positive. Yes, of course, the values for our summation should be n equals 1 to infinity. Let's make sure and fix that. And so we have 1 over n absolute value of x to the n. The power of the absolute value is the absolute value of the power. And so absolute value of an plus 1 can be written as 1 over n plus 1 times the absolute value of x to the n plus 1. And so the L that we would use in the ratio test is the limit as n goes to infinity of this divided by this, and a little bit of cancellation here. I'm going to cancel some powers of the absolute value of x. I'm going to cancel some power, not cancel any powers of n, but combine them together, and we end up with the limit as n goes to infinity of n over n plus 1 times the absolute value of x, once I cancel the powers of x away. Now as n goes to infinity, this piece goes to 1. And of course the absolute value of x all by itself has no n's in it, so we end up with L equals the absolute value of x. Now the conclusion that we get from the ratio test is that the convergence or divergence of this series depends on the value of L. So this series, summation n equals 1 to infinity 1 over n x to the n, converges when L is less than 1. So when absolute value of x is less than 1, and it diverges when L is greater than 1 That is, when absolute value of x is greater than 1. So we've found a whole bunch of x values that make this series converge, namely the ones up here. Now there are a couple of cases that we have left to deal with, right? The ratio test is inconclusive when L is equal to 1. In other words, when absolute value of x is equal to 1. In other words, when x equals plus or minus 1. So we have to treat these cases separately. So the case where x equals 1, in that case our series is of the form n equals 1 to infinity, 1 over n times 1 to the n. So that's the summation n equals 1 to infinity of 1 over n. That's harmonic series, which diverges. And when x equals negative 1, our series is n equals 1 to infinity, 1 over n minus 1 to the n. This is the alternating harmonic series. And if you haven't seen this one, you can use the alternating series test in order to decide that this one converges. So the x equals negative 1 piece gets lumped in with the points where the series converges, and the x equals 1 piece gets put in with the values where the series diverges. So in other words, the series diverges, I'm interested in it converges exactly when x is in the interval from negative 1 to 1, where we include the left-hand endpoint because of the alternating piece here, and we do not include the right-hand endpoint because of this piece here. Now, some things that are important to note about this is that this range of x values where the series converges, this is an interval. And in fact, this interval has a special name. It's called the interval of convergence. Okay. And now what we're in a position to do is to talk about power series in general. So, power series is any series of the form summation over n of Cn times x to the n. Okay, so this is one form of the series. We'll talk about the most general form in just a minute, but I want to just talk about the special case right now. Now, some things to note about this series are that this always converges for x equals 0, right? If you plug in x equals 0, then all those x to the n powers just become 0, and you end up with a nice finite sum. And then the question becomes, what about other x values? And there's a result in the textbook that tells us that there are exactly 3 possibilities. The first possibility is that it converges only for x equals 0. And the second possibility is that this series can converge for all x values. Obviously, these both can't happen simultaneously, so the first one or the second one. Or the third possibility is that it converges exactly on some interval centered at x equals 0. So there are 4 different types of intervals that we're considering here. We can have the closed interval from negative r to r. We can have half closed, half open from negative r to r, or half open, half closed, or entirely open. So this is what we mean by an interval centered at x equals 0, right? So as you saw in the previous example that we did, we had an interval from negative 1 to 1 that included the left-hand endpoint, but didn't include the right-hand endpoint, so it was just like this one. And there are lots of examples to show that other possibilities can occur. The interval that occurs here, this is called the interval of convergence. For the power series. And one finds it exactly in the same way that we found the x values that make the series converge. That's exactly what the definition is saying. So we find this exactly like we found the interval in the previous example. And this number r is called the radius of convergence of the power series. So in the previous example, we had r equals 1 because our interval went from negative 1 to 1. That's what happens in case 3. In this case 2, we say that the interval of convergence is the interval from negative infinity to positive infinity, or if you like, you can use the bold R for the set of all real numbers. And in this case, we have the radius of convergence is R equals infinity. Make sure to notice the difference between the two R's. One has got 2 vertical bars and the other one has just a regular one. In this top case, usually we don't talk about the interval of convergence here, but you can say, if you'd like, the interval of convergence goes from 0 to 0, which is kind of weird. Mostly we talk about the radius of convergence in this case, which is 0. More generally, you can have power series that aren't centered at x equals 0. You can have other power series that look like this. So we have a summation over n coefficients Cn times x minus a to the n. And in a series like this, you'll still have a radius of convergence. The interval of convergence will be centered at x equals a instead of at x equals 0. And you should look at the theorem that's on page 743 of the text. That's theorem 3. That explains exactly what the intervals of convergence and radius of convergence look like in that case. And you should also look at the examples in the text. Looks like there are 5 of them, to give more examples of actually computing those intervals. Right? So this is the end of the lecture on section 11.8 on power series.